ionized it by shooting it with an electron gun. So now it's positively charged. That positively charged particle was accelerated A through an electric field, deflected D through a magnetic field, and finally detected by virtue of its mass to charge ratio. Remember that? Mass to charge ratio? Anyone?
Mass to charge? Yes.
Okay, again, you're never going to be assessed on it, so. This is a model of what you might get out of a mass spectrometer if you put a certain element in it. You would get on the x-axis the mass to charge. We're going to assume that the charge of everything is +1. An uncharged species would not be accelerated, deflected, or detected. It would be silent. A negatively charged species would go backwards. That would be right out. So all we're going to see is positively charged, and we have a bunch of very clever people in this world who work pretty hard to make sure it's just +1. So this is just supposed to be the straight up mass. This is going to be the intensity or the number of atoms of each of those masses. And so we are able to use data like this in a multiple choice question to find the relative atomic mass of boron. Yo. Audrey is nodding. She has acknowledged that she has learned how to do this in her life. So is the average mass of boron closer to 10 or 11? Because there's more of them. So it's really a weighted average. And so we said 19 of the 100 atoms had a mass of 10, while 81 of the 100 atoms had a mass of 11. And so then,
Did we do this last year?
yes, that's what I'm trying to say. Remember chapter 2.
Yes. What was this? Like what first?
And you gotta be able to do that in your head, but I'm afraid that some of you are gonna cry and some of you aren't gonna be interested, so you gotta get 10.81 out of that. Hopefully, if you look at boron, it's 10.811. We've done a fine job. Good on us. You can do the inverse of this if you're so inclined. You can know that the mass of bromine is just about 79.9. Know that it exists as two isotopes and try to find out the percentages of each. Which one is there more of, 79 or 81?
Also, wait,
Why, Remy? Because it's closer. And so you set up something that's like 79.90 is equal to x times 79 plus 1 minus x times 81. And you solve for x, and you're going to get that it's 55%, or 0.55 is a fraction. 79 bromine, and 45%, or the fraction would be 0.45 of 81 bromine. So it's just algebra. Some of you might remember that the algebra is not terrible. Some of you just want to forget it. Mohab, do you remember this? Audrey, do you remember this? Or can you remember this? Okay, chapter 2. This is not what we're doing in chapter 11. In chapter 11, we're not interested in atoms, but we're interested in whole molecules. So instead of putting boron in there and looking at the different isotopic abundances of boron, something no one actually has interest in, what we're going to do is we're going to put a big molecule in there, but we're going to go through these same processes. We're going to get that big molecule into the gas phase, and we're going to hit it with an electron gun to ionize it. What's different in a big molecule is that when you hit it with a really high energy electron, not only can you remove an electron, but you can also fragment the molecule, break it into pieces. We're going to use the pieces, the masses of those pieces, to try to build the molecule back up. So that is what we're going to do today. We're going to think about how the masses of the fragments allow us to determine what organic molecule we have in mind. So let me just show you one. I'm doing the one on, no, I'm not. Don't know of another example. Hey, Morgatron, I'll just do it. So this molecule is propanol, and I'm going to draw the structural formula of it just to help us see what's going on. Again, on the x-axis I have the mass to charge ratio. On the y-axis I have intensity. While in chapter 2 we focused on intensity to do a mathematical calculation, In chapter 11, the intensity axis doesn't matter. What's going to happen in chapter 11 is that certain values will be numbered or starred, and those are the ones you've got to worry about. If it doesn't have a number or a star, nobody cares. The fragmentation is really actually quite hard. We have very high energy gas phase ions being blown apart into pieces, and they do a lot of weird things. Atmospheric chemistry is really challenging, and so you'll get some masses here you can't identify because of reorganization within the molecule, and this is one of those times where it just doesn't matter. Like, they will pull out the ones that we can understand. Margaret was kind enough to hand out chemistry data booklets, and today the page you want to focus on is going to be in the 20s. It's going to be 27. So for this particular molecule, what you're going to find is that the biggest mass peak is found at a mass of 60. The peak that is farthest to the right is almost always referred to as the parent peak, or the molecular ion peak. That's what the M stands for. Why does it have to be a molecule? Yeah, I thought that was a good question. I don't know, maybe it's not a good question. It felt good when I was asking it. Could I put salt into a mass spectrometer? So NaCl is a molecular, right? It's ionic. So NaCl is made up this like nearly infinite lattice from the perspective of atoms of alternating sodiums and chlorines. And so if I were to break it apart, I wouldn't see a peak at 58 like I might expect. I might be able to get a sodium fragment to fall off, but getting an ion into the gas phase is really hard. We know that here we just have intermolecular forces that are holding these molecules together. So it is reasonable to me that we could get it into the gas phase to do this chemistry. So I need something that will go into the gas phase and something that will have a formula that's meaningful. I'm not looking at an empirical formula here like NaCl, I'm looking at the actual molecule. For those of you who go on to do drug design, they do have really big molecules for drugs and for like things that your body turns those drugs into. And so they have very clever ways of getting things into the gas phase, but the gas phase is like an absolute here. So we talk about MALDI, matrix-assisted laser desorption ionization. Like they put this stuff into a white matrix and then beat on it with a really high energy laser to convince some of it to fly through the instrument. It has to be a molecule. That was a long story. It has to be a molecule. Okay, so the rightmost peak, the parent peak, has a mass of 60. Does that make sense with our structure? So we're going to take 3 times 12, it's 36. We're going to add 16 for the oxygen. We're going to get to 52. We're going to add 8 hydrogens. That's going to get us to 60. The parent peak is really just all of the 1-propanol with a plus charge on it. If you do not write the positive charge, you do not get the mark. So I will be ruthless, they will be ruthless, but we will practice this. The only way you can see this is if the charge is 1. Remember, this is the mass to charge ratio. So very often, the peak that is farthest to the right is the parent peak. Right next to it, in this particular spectrum, there's a short line at about 59. What is the distance between 60 and 59? So what do you think has been lost by this molecule? A hydrogen. So I think that this loss of 1 represents this structure, C3H7O+. Now if Rainey wanted to be stubborn, and she wrote this, implied that it was one of the hydrogens on the alkane that fell off, I don't think she cares which one, I certainly don't. Instead of the OH hydrogen, these two things have the same molecular formula. Both of these would be considered correct. In my experience, I believe that it's going to be the hydroxyl hydrogen that falls off. It makes sense to me. It's consistent with having only one peak that's one away and not a whole lot of peaks here that are rando hydrogens falling off. But there are no marks really associated with you guessing the correct structure of the fragment. You just need to know its formula. So this would be acceptable, but I believe this is correct. So we have lost an H. Another peak that is pointed out here is a peak at 43. The most important thing I'm going to say to you today is that when we are looking for the difference, this is not sequential. We're always going to go back to the parent peak to subtract. So it's not like this molecule has lost the hydrogen and then. Instead, one of these molecules lost the hydrogen and hit my detector. Another one of the mole of molecules that is inside my machine didn't fragment that way. A different molecule in my machine lost 60 minus 43. Sounds like 17. And so we're going to look in the table, and we see that the fragment most associated with 17 is OH. So I believe that my molecule has lost an OH, and so my molecule is going to be C3H7 plus. The next peak that I observe in my spectrum happens around 31. Quite tall. Again, this is not a sequential process. I have another molecule that has fragmented. This molecule has lost 29. If a molecule loses 29, the table, my data booklet, tells me that it lost what? Either an ethyl group or a CHO, yeah. So which one is it? Do we know if it's an ethyl group or a CHO? Well, because this isn't an aldehyde, I don't think I can lose a CHO. So because we've come into this knowing what the molecule is, I think that we can be pretty confident and say this time it's an ethyl. But in a normal time, we might have to have sort of two paths. We might say this is one or the other. Could we determine between the ethyl being lost and the CHO being lost if we used an IR? Because we could find evidence of which one. We could find that carbonyl group inside an IR. So if there's another piece of data, we might have a way of saying, oh, it seems kind of likely it was a CHO. In this case, where we know we don't have that carbonyl, it's probably going to be the ethyl, and so what we've got here is a CH2OH plus. So I've just cut off that ethyl, and I've left that side of the molecule, the CH2OH plus. Next up, here, hold on. There's a peak at 29. So that's a loss of 31. The loss of 31 is the loss of a CH3O. If I lost a CH3O, that would be that same fragment, but I'm seeing the other half of it. Something with a mass of 29 is going to be the ethyl group. I approach this when it's a small molecule, as I've shown you. I choose the parent molecule and I subtract everything to figure out what is most likely left over using my handy dandy table of likely fragments. If the molecule is bigger, sometimes my table isn't big enough to include all of the stuff. And so I would suggest that another way of using the fragments is it is conceivable that a mass of 29 that's in my table as an ethyl being lost could also be an ethyl being found. So I would suggest that if you see peaks that you associate with 45, 31, 29, you consider just writing down what's in the table with a plus sign. Again, if you see it here, it has to have a plus. There is no guarantee that if you see the 31 half of the molecule, you'll see the 29 half of the molecule. There's no guarantee that both sides will carry the positive charge. You can imagine that the positive charge is more stable in some instances than other instances, and as such, you just take whatever they tell you is there and use it. This is puzzly, but if you look at the actual spectrum that I was describing, again, it's about the 4th page, maybe in the notes I gave you today. There are a lot of lines here, but they only pointed out the ones that they thought that we could address. And that's how it will always look. Hey guys, these are the lines that we can use to establish what shape this is. Do you think this would be different if we had a different alcohol? It would? So would the IR of 2 alcohols be different in a way that was meaningful to you?
Because if you're still doing the same distance or whatever, you're still going to remove the same, like, the Joe or the OH. But it depends on what alcohol it is. Because with propanol, you can lose the ethyl and still have something, but if it was an ethanol, you lose like everything.
That's right. So mass spectrometry is going to give us a new technique because it is going to be able to distinguish between skeletal and positional isomers. Things that are different lengths are going to have different fragments, and sometimes things with different positions will have different fragments. So IR of 2 alcohols would be, for our eyes, the same. The fingerprint region would be different. So if we had a list of spectra, we could say, oh, well, that's not propanol, but like I can't tell which alcohol I've got. But with the mass spectrum, there's a chance to be able to decide which alcohol I've got.
You said between skeletal and positional?
Because the IR couldn't do that for us. Do you want to try one on your own? So you can try to identify the different things that are in propanal. Propanal only has 3 big peaks, but one of them is new. So propanal is on page 2. The second half of the document I gave you, the first half is IR, the second half is mass spec. Marachi, what's your major?
It depends on, like, some, like, basically just like biology, but some schools are doing like human biology, some are doing, like, biochem, or like, nuclear bio, or like, I think even in one I'm doing like, bio concentration in like A and B. Are you close to, are you still eating, or? Probably not, because tuition is really expensive. I'm just looking out for like scholarships.
Yeah, I wish there weren't those 2 steps of getting into school. And should you choose to practice medicine, do you know what you want to do?
What do you want to do?
Yes, I wanted you to do B. B is propanal.
Which med thing? Sorry? Which med thing do you want to do? Oh, dermatology.
So, I mean, you guys can imagine that I was looking for some better materials on mass spec than the ones I had. The ones I have talk too much about the chemistry that goes on in the fragments, and we don't have to learn it. So I found this, and then I found that the same guy made something on IR. I was like, oh, this is nice, I'll print that too. sorry, so the identity of the fragment is what has the positive charge, and then what fell off is the other answer. Sophia, what do you think the peak of 58 is?
What do you mean,
What?
like the identity of the fragment?
Yes, what is the identity of the fragment for the peak of 58?
H5CO plus.
Say that again?
C2H5CO plus.
I don't think you counted right.
Yeah, CO plus.
So if I add that up, I get 29, and then I get 12 more is 41, 57. This is 58.
Okay.
This is the second, this is 6 page.
Oh,
C2H6, CO+.
Okay, I'm not gonna write it as C2H6CO plus because I know it's this molecule. So I'm just gonna write it like a condensed formula, but again, no one would mark you wrong for moving that hydrogen around. That is the parent peak, so I'm just trying to write exactly what this is with a plus sign. It's lost nothing. That is the parent peak. That is the molecule making its whole way.
Oh.
The electron got shot in, but all the electron did was remove a single electron. What?
I thought the parent was 59.
That says N plus one.
Is that there?
Okay.
Oh, it says N plus one.
So it asked you what 58 was, but then I said, oh look, there's that extra little peak here. So what do you think m plus 1 could possibly mean? That's not what it means, but that's the right mass. Reasonable thought. Why are we all mumbling today? You are not quiet. Yes, parent peak plus 1. Elizabeth thinks it's plus 1 because of the hydrogen. I said you're right, it's plus 1, but it's not because of the hydrogen. Then you talk. Okay, then you talk.
I just thought it was on this one.
That is correct. Okay, that's fine. Anyone have any thoughts about why we might have an M plus 1 peak? Could anyone tell me what the relative atomic mass of carbon is? Well, that's not the relative atomic mass, that's the atomic that's the mass number.
Oh, I don't know what it is, but
12.011?
oh.
I ain't asking you to memorize something. And I said not the mass number.
Isotopes.
Oh, Quinn. Carbon and hydrogen have naturally occurring isotopes. So there's some amount of carbon-13, about 1% in the world, and some amount of hydrogen deuterium, we call that one. And because of the naturally occurring isotopes of carbon, especially as a molecule gets bigger, we'll sometimes see a really tiny peak built in due to the natural isotopic abundance, I'll say of carbon-13. So instead of that being an extra hydrogen, what it really is an extra neutron. So every now and then one of those carbon atoms just happens to have an extra neutron. That's why the mass under carbon isn't a straight up 12. And that's why sometimes you'll see like a little shadow peak that's a little bit bigger. In truly big molecules, you can get an M plus 2 peak. Really, really tiny. Sometimes if you have interesting molecules, I know that In Thinking likes to do this, and we'll do that next class maybe. Like bromine, there is no such thing as bromine that weighs 79.9. There's bromine 79 and bromine 81. So you'll actually get two like reasonably sized mirror peaks to show the two isotopes. So these are specific molecules, that's why they have integer mass numbers. Okay, so what do you think the 57 is? That's right, I think I lost that aldehyde H. This is a loss of H. And And so the fragment that's present is everything but the H. Then the next one I get to is 29. Again, I'm gonna measure it from the parent peak, from 58. 58 minus 29 is a loss of 29. So that could be a loss of two things. It could be a loss of a CHO or an ethyl. So which is it? What do we write down?
Sure.
Okay. We can write down either one. They're both correct. So this molecule essentially just breaks in half. The left side weighs 29, the right side weighs 29. And so you could call this peak either CHO plus or ethyl plus. And you lost the opposite. Both answers would be 100% acceptable. We don't know which one is going to be better at accepting that positive charge. Amarachi.
Why do we start the subtraction from the 50 and
So the M+1 is just evidence that every now and then we get a carbon-13. That's not most of the molecules, it's just a special molecule or two in there. So an IB question will be like, why is it there? You say isotopes, and then you just ignore it. So when we start a problem, I would recommend two things. Either, if you know what the molecule is, just figure out its molar mass. Just add it up, get the 58. Or, if you don't know what the molecule is, say you only knew its empirical formula, look for the tallest peak furthest to the right. So if you see a little tiny one, now you know that you can ignore it, especially if it's labeled M+1, but look for the tallest peak to the right, and that's going to be your best guess as to the actual molar mass of the molecule. Ready for another one? Think this is easy or hard? Mood is bad today.
It's okay.
Okay, so this molecule is pretty massive. So one more time, you can see 136 is numbered, but there's a little bit of evidence of something to a bigger mass because of the natural isotopic abundance of carbon-13 or deuterium. You can see that only 3 of these peaks are numbered, so we're not going to worry about anything else because we don't have to. Now this molecule overall is meant to be an ester. It's meant to be methyl benzoate. And we're trying to understand how to ascribe these 3 peaks to that structure. So the first thing I'm going to do is think about the mass of my overall methyl benzoate. And I feel lazy, so I'm ready just to say that 136 is probably my molecule. But if you don't feel lazy, we could say that we have 6 carbons here. We have 5 hydrogens here. We have the carbonyl, we have the oxygen, and we have the methyl. So if we add that, we get 72 and 5 more is 77. 77, 85, 105, 120, 136. So it works. Yay! So again, all I've done is try to write a structural formula. So I made benzene into C6H5. I wrote the kook, that's the ester, and I've ended it with that methyl group. Put a plus sign on it because if it's visible in a mass spectrum, it has to be charged. And the first thing I find is that it is possible for this molecule to lose 31.
31.
It's possible for this molecule also to lose, that's 2359.
But you just add the differences. Like 59, you just add the groups that would be lost in 28 and 31.
No. In this case, yes, but not always. So instead of it being sequential, I always just want to compare it to 136. There's no requirement that the 31 lost here are also lost here.
I just mean like when finding like the quantity on the bigger table, if it's like bigger than like the
would say that this is the one that I would add to the table, for what it's worth, but it's just not there. So what do you think the loss of 31 can be? And remember, we have the molecule to look at. Right, I think it's just gonna be this right here. And so that's gonna leave me with a carbonyl on a benzene. So it's a loss of OCH3. So C6H5CO plus. And then Amarachi's seeing the 59 and she's trying to figure out how she can use the table to try to establish what that is. And it's gonna be hard, right? Because I don't see it in the table. You could see it in the molecule, or what you can do is try to think about in terms of masses what makes sense. So what is the maximum number of carbons that we could have in 59? So 5 carbons would weigh 60. So this would be 4 carbons, so that would be 48. And that would be 11 hydrogens. And I know butane is C4H10, so that's some nonsense. So what if it was 3 carbons, 1 oxygen? How many hydrogens would that be? So I'm gonna take 3 times 12. 42, 52, 7 hydrogens. Trying to make my numbers look numbery, sorry. Is that reasonable? Do we have anything in the molecule that is consistent with 3 carbons, 1 oxygen, and 7 hydrogens? I would say we do not. So let me try to have 2 carbons, 2 oxygens, so that would be 24, and 32, that would be 56. So I think I would need 3 hydrogens. And so I think if we look over here, we're gonna find that that's what we have. We have 2 carbons, 2 oxygens, and 3 hydrogens. I don't ever wanna be in a place where I have to do this, because this kinda sucks, right? Like this is just straight what numbers add up to 50 whatever. It's not me feeling smart. So Morgan, how did you come to this conclusion?
I looked at the structure of the molecule and thought, common sense, what am I gonna lose? What is most likely to be lost? And it would be the CO as well as the OCH3. Just that functional group over there.
So I think that they should add into the table that the benzyl fragment, the phenyl fragment is 77, but it's not gonna be in the table when you take the test. Like no matter how many times I think it ought to be there, it's not gonna be there, so. Benzene rings are pretty easy to find. Do you remember the IHD of benzene? How many rings and double bonds does a benzene fragment have? It has 3 double bonds. How many rings? 1 ring, so 4. So its IHD is 4. So one way of identifying, hey everybody, we got a benzene, is by looking at the IHD. If we can just see that there is like a whole lot of carbons and not too many hydrogens. Another way of identifying that you have a benzene is anytime we have a mass that's this big, like it's just got to be in your thought process. If I have a mass over 80, maybe I want to think to myself, is it possible that I could have a benzene here? I don't know. Okay, let's try this one. You have acute ester, ethyl ethanoate. Add up the total mass, we're gonna get 1529 seems so easy and then I do it. Numbers, 88, look. Then counting from there backwards, or perhaps looking at the fragments themselves, do you think you can identify what the other 4 values are? Morgan seems to think you can do this.
Seem to think that I can.
Is it not going well?
Trying to figure out what the 45 is, I can't remember.
I mean, I hope that they cry a little bit with the loss of 45. We'll see how it goes. I haven't
be a
seen adequate struggle today.
That doesn't make sense.
You wanna look at the big
Correct, it doesn't make
What?
sense.
Yeah, it could be a coup, but it doesn't make sense. Draw it out. Draw this first. Draw it. Let's rotate it.
Okay, so starting from the right, I just put down the plus sign on the whole molecule because I expect that to be the parent peak. And then it was easy to take 88 minus 73 is 15, so I lost the methyl. A DT doesn't matter if I lost a different methyl than you. No. Like there's methyls on either end of that molecule, and I just took one off. I took the one that was convenient for my writing. But as long as we have the same overall formula, we're good. The loss of 45 is a little bit disheartening to me because they do not have a carboxylic acid here.
Yeah, but it's in the
Sequence.
I'm just gonna go with that.
No, you can't just go with that because it doesn't make sense.
So we're just looking for a fragment that's inside the molecule to fall off. We're not trying to be creative. What does that mean?
No, can't be that even.
So if I broke it there, I got the 73. If I break it there, I don't actually seem to see that peak. That would be 31. 31 would be 57. I don't have a peak at 57. What would it be if I broke it there? That would be too many. What if we count this way? What is 29 and that? Why did this work for me when I was alone?
I think you're gonna lose a 15.
Oh, it's because I have the molecule backwards.
Yeah. 15, 14, 16.
What molecule did I draw?
I think the right one.
Can't even draw backwards. Okay, so I fixed it there. Well, you didn't even tell me what molecule this is. Like backwards. Yeah, I got methylpropanoate up here. I'm ready to cry because this isn't working. I tell you, this will find, positional isomers because we just found one. So let's draw the molecule like your teacher's not, out of their mind. And see if we can do any better. Does it have a coup now?
Yeah.
No, it doesn't.
No, it doesn't. What would you do?
Well, I'm not ready to cry yet. sure.
15, 14,
Sure.
16.
Okay, so I'm gonna just start looking. This is 15, this is 29. 29 and 16 is 45? Does that actually weigh 45?
Yeah.
24, 29, 45.
14, 15.
I thought you know the CH2, CH3?
You take off the CO.
16 plus
16, 14,
24, 40 plus. Oh, it does.
I think you're
So
right.
I believe this is CH3CO plus. I mean, that's what I figured out when I was, not embarrassing myself with you, but instead, sitting in the privacy of my own space. Not stuck in. Oh, so this is a loss of this, sorry.
So, oh yeah, this is
So it is CH3C
Wait.
H2O plus. It's a loss of 45. This adds to 45, it is 43, this adds to 43.
Gotcha.
No, wait. Because you're losing the CH3, CH2O. Because you're losing the 45.
Oh no, what did I?
Yes.
26 and 15,
It's the same thing.
28 and 15 is 43. Yes, I did that.
So it was the.
Hey, you're always right, Amarash.
No,
You're always right. No, I did it right on my paper and I just got dumb when I walked in the room.
To make you feel better, my first guess was ethanol capsule with the plus on it, so.
Like, we're all struggling. I'm gonna count again, just so you don't, judge me too harshly. So I'm just gonna make sure that this has a mass of 45. So this is 15, and 15, and 15. This is 45. This is what we lost. This is supposed to have a mass of 43. This is 15 and 28. It's good. Everything is good. The world is a better place. If the IB didn't hate you, what might they put next to COOH in the data booklet? This thing.
So they do
They
That's
do.
why they left us with the COH.
So they tell you it's a loss of COOH. All of us were sad because there wasn't a COOH. Then we were sadder because I can't draw a molecule or add. I totally lost track of things. But upon drawing the right molecule, we at least could make a fragment that had the right mass. We made a fragment that had the right mass, and we made a loss that was also the correct number. The rest of them are thankfully easy. Thankfully. I'm kind of tired of subtracting, so I thought maybe I could cheat from the data booklet. Do we associate a fragment with 29 that's present in this molecule?
Yes, CH3,
Right, I think it's just gonna be this right here, so I'm just gonna write that down. And of course, the methyl is what we find at 15. So I frequently will subtract until the numbers get small, and then I will add from 0. Like, this is a fragment I can identify because it's written in the table.
Is there a reason why they don't put, besides they hate you, is there a reason why they don't put the CH3, CH2O?
That is the reason.
Why do they have to make it different? We're just trying to pass.
We're just trying to.
Dude, I'm just trying to add. I can't even do that. I'm gonna have to take, arithmetic SL, arithmetic ab initio. Okay, I need redemption, so we're gonna do one more of these. What? We did. I just drew that straight on the board. I didn't show you. I just said you had it, and then I decided to project because I was trying to be a better sport. I just totally arted 1A. I did a fantastic job, though. Okay, so keep me honest. Don't let me draw the wrong molecule because things get terrible. So here we have two esters. We're going to try to tell the esters apart. All Amarachi taught me that the esters are ethyl methanoate and methyl ethanoate. I'm going to try to remember that. They're ethyl methanoate and methyl ethanoate.
So the first part comes from what's not attached to the group?
The first part comes from what's on the ether side, so this is methyl ethanoate.
Okay.
And then I have to draw you. Yeah. Why are you confused?
I just can't tell them apart without the labels.
Whatever is on the C side of the coup.
There's C's on both sides.
No, on the C side.
We
of
talked about the
coup.
carbonyl side and the ether side.
Sorry, the carbonyl side. I call it the C side of the coup.
Yeah, I understand, but
That's the ill.
What's attached to the double bond?
no, what's attached to this is the ill.
I'm sorry.
What's attached to
That's
the
what I meant.
ether is the ill. The 8 is attached to the double bond.
Yeah.
You're getting me confused with the carbonyl side.
Carbonyl.
The C side is the OH. It's got the O's.
Okay, does the parent peak reveal anything about this problem?
No.
Because these are structural isomers or positional isomers of each other. This peak tells us nothing. So who knows?
That's 6 or
No.
It's a 6 if I didn't mess up. So I seem to be able to lose 15 and 29. I have a peak at 15. That should be a methyl cation. Both of these have that, so I'm not sure that's really great. So the question is, which one of these can lose in 29? So it does have a CHO. Isn't that crazy? Amarachi has just said the craziest thing. She said this ester has a CHO, which is like anathema to me, right? But she's right. Right, esters don't have CHOs. It's terrible. But she says that she sees the group of a C, O, and H, and that has a mass of 29. So she can imagine that if this broke here, she could lose 29 and be left with this portion of the molecule. Go ahead. What? Why don't that add up? Say that again?
74 minus, to get to 74 to 43, that's 31.
Math is so hard today.
Yeah, I have 31 written down. I didn't want to change
Hey, someone else is in charge of the ab initio arithmetic. I'm done with it. Or I just gotta hold my notes in my other hands. Like,
Did not sleep last night.
I didn't sleep either. I thought it was like a statewide thing.
Thanks.
Nationwide non-sleep.
Like I figure you guys just miss school so much. You're so excited to see me. You're like, oh, I'm counting the minutes. You had your 5-day weekend,
I
right?
really did enjoy the 4-day weekend, and I think we need more of them. It was 5.
You were out of school
I
on
mean,
Thursday.
true, but like I was working on my Psych A like on the bus there and back, so I didn't even feel like a day off.
You were out of school.
I would not have been working on
Oh, did y'all go on like a field trip?
Redemption didn't go great for me.
That is the
Better in mathing alone than I am in a group.
Here, I'll just be totally silent. You can all tell me the answer to the next one.
I don't know what's which one?
It was methyl ethanoate.
And how did you get something that?
Because 86, shit, that's the wrong number. Because 74 minus 43 is 31. So it had to lose a CH3O group, 31. The CH3O group is this group right here, and this is methyl ethanoate, so,
Question,
yeah.
could it have also lost the CH3CH2?
That's 29.
No, sorry, that's.
Yeah,
I'm done.
don't get me started. So that would have made it this. This can
Yeah.
lose a 29 there or a 29 there.
Gotcha.
And so that would have made it this. And so like I was quite content with our answer, right? It was a solid answer. It just was not the question that was being asked. So we're looking now at pentanone. It can be 2 pentanone or 3 pentanone, and you're gonna try to tell me which pentanone it is. I'm pretty boss at naming them at least still.
I hope this is his open. This is the one that's open.
Well, if I ever find this guy, I'd be like, give me a key. So I'm just gonna take a vote. Is it 2 or 3? And I'm gonna take that vote in about 3 minutes. Your two choices are 2 pentanone and 3 pentanone. 2B? Yeah, 2 pentanone, 3 pentanone. Yeah, that's you. She misnamed it. She's perfect, but she made a mistake. And she's allowed. For what it's worth, Audrey, I agree. You're gonna write down C5H10O.
Oh, I have it open here.
Come on, people. This is my answer.
It's living. Yeah. Death will be, I mean, it's not exactly a part of life, but in a way it is a part of life, Yeah. It is a part of life, but it's like really separate, Okay, I think it's the two.
What is your justification?
Because 43 is this end. It's this part. 43 is whatever part this is.
Was it 2?
The one with the O.
right?
Yeah.
Oh, because
Yeah. I hate this one.
What?
It's so much writing.
So much writing. It's like a puzzle.
Yeah, but
Puzzle.
The writing.
Puzzle.
I don't think I've made any mistakes. Take it if I have. I tried to identify the 3 fragments by what they were. I didn't write down what was lost. But hopefully you'll agree with all the people who have forwarded answers that it's most likely 2 pentanone. Both of them could lose a methyl, but it's kind of nice this guy has a methyl. This one is the only one that can lose that propyl fragment or the CH3CO. It's kind of your call as to what it's lost and what is present. For homework, can you do number 3? I just think the bell's gonna ring before we finish it.
Yes.
Wait, 10 seconds. Oh, you look fantastic.
And so in that one, you get a sense of how they make this a multi-part question. They give you some mass percent data, they give you some IR data that's a little too leading, and then they give you the mass spectrum. So that's where we're going. And next class, we're gonna learn about nuclear magnetic resonance spectroscopy, MRIs.
Do we get back our test?
I mean,
Because someone's taking it later.
yes, people are taking it later, like,
I will make sure to give them.
You will what?
Make sure to give them that.
So they can like,
Practicing on the table.
yeah, I would say that way, since you let me.
You made that joke. You made that joke.
You're connecting the dots, but I didn't.
I always knew you were creative, man. Yes. Very creative. Just like sound.
Oh, you use lemon.
Why would you use lemon work?
Can you tell me more about the sound incident? Like, that was.